Hello, and welcome to Sleepy Engineering. In this video, we will explore the complete history and function of one of the most important sources of renewable energy in the modern world, the hydroelectric dam. This narration is intentionally slow, detailed, and repetitive. It is designed to help you relax, focus, or fall asleep. There will be no sudden sounds, no music, and no emotional tone. Only the steady voice of information. Now, please sit back, close your eyes if you like, and let the story of the dam and the hydropower plant begin. Hydropower is one of the oldest and most reliable sources of energy harnessed by human civilization, and it has played an important role in the development of communities, industries, and entire nations across centuries. When people think of renewable energy today, they often imagine wind turbines with their tall white towers spinning against the horizon, or solar panels glimmering across wide fields and rooftops. But long before these technologies were introduced, water was already serving as a driving force for human progress. From the earliest water wheels used in ancient civilizations, to grind grain or power simple mechanical devices, to the massive hydroelectric plants of the modern era, water has remained a constant partner in humanity's attempt to transform natural forces into usable energy. At the most basic level, hydropower is made possible because of the potential energy stored in water as it moves from higher elevations to lower elevations. Gravity pulls water downhill, and in doing so provides a steady flow of energy that can be harnessed to perform work. This principle is simple yet powerful, and it has allowed human beings to extract energy from rivers, streams, and reservoirs in ways that have shaped both technology and society. In today's world, hydropower accounts for a significant share of global electricity production. It is considered the largest source of renewable energy worldwide, surpassing both wind and solar in overall contribution. Countries such as China, Brazil, Canada, and the United States rely heavily on hydroelectricity for meeting national energy demands. In some regions, such as Norway, hydropower provides nearly all of the country's electricity, demonstrating its potential to be not just a supplement, but a central foundation for an entire grid. Unlike fossil fuel power plants, which depend on coal oil or natural gas, hydroelectric dams do not consume their fuel in the same sense. The water used to generate power continues downstream after passing through the turbines, and it is not depleted by the process. This makes hydropower both renewable and sustainable as long as rainfall and natural water cycles continue to replenish rivers and reservoirs. Another major advantage of hydropower is its ability to respond quickly to fluctuations in demand. Unlike thermal power plants, which may take hours to start up or shut down, hydroelectric plants can adjust their output in minutes simply by opening or closing gates that control the flow of water to the turbines. This flexibility makes hydropower an ideal complement to other renewable sources such as wind and solar, which can be intermittent depending on weather conditions. In addition to generating electricity, dams and reservoirs created for hydropower often serve multiple purposes. They provide water storage for irrigation, which supports agriculture in arid regions. They offer flood control by capturing excess water during rainy seasons and releasing it gradually to prevent downstream flooding. Many reservoirs also become recreational areas where people can fish boat or swim, and they sometimes support tourism that benefits local economies. Yet while hydropower has clear advantages, it also comes with important challenges and environmental considerations. Building a large dam alters the natural flow of a river, and this can disrupt ecosystems, affect fish migration patterns, and flood areas that were once fertile farmland or inhabited communities. The social impacts of resettling populations to make way for reservoirs have been significant in some parts of the world, leading to debates about the balance between renewable energy generation and human or environmental costs. Modern hydropower planning increasingly takes these factors into account, with efforts to design dams that minimize ecological disruption, such as fish ladders or bypass systems. And with a focus on evaluating whether new projects are truly necessary, or whether existing dams can be upgraded for better efficiency. Despite these concerns, hydropower remains a cornerstone of global energy strategies. It provides reliable baseload power while also serving as a backup for grids that are increasingly integrating variable renewable sources. In the context of climate change, where reducing carbon emissions is a global priority, hydropower offers a way to replace fossil fuel generation with clean renewable electricity that produces little to no greenhouse gases during operation. Furthermore, hydropower can support electrification in regions that are still developing. Many countries in Africa and Asia, with abundant rivers and rainfall, see hydropower as a path to greater energy independence and economic growth. By investing in dams and hydropower plants, these nations can provide electricity to rural communities, stimulate industrial development, and raise living standards. The global importance of hydropower is not only measured in electricity production, but also in its role as a stabilizing element in the transition to a more sustainable energy system. Its reliability allows it to anchor power grids that might otherwise struggle with fluctuations from newer renewable technologies. Its widespread availability makes it a resource that can be tapped in diverse geographic locations, from mountainous terrain with fast-flowing rivers to flat regions where large reservoirs can be constructed. As we explore the history, design, and function of dams and hydroelectric plants in the following sections, it is important to keep in mind this dual nature of hydropower as both an ancient technology and a modern necessity. It connects the ingenuity of early civilizations with the pressing needs of today's societies. It demonstrates how a simple principle, harnessing the force of falling water, can scale from small village mills to massive installations that power millions of homes. And it reminds us that while energy can be extracted from nature, it always comes with choices about how to balance human needs with environmental stewardship. Hydropower therefore stands as a symbol of both promise and responsibility in the continuing story of human progress. By looking closely at how it works and why it matters, we gain insight not only into the mechanics of turbines and reservoirs, but also into the broader challenge of building an energy system that is sustainable, equitable, and resilient for generations to come. The history of dams and hydropower plants stretches across thousands of years and reflects humanity's continuous effort to master water as both a life-giving resource and a source of power. The earliest civilizations recognized the importance of water management long before electricity was ever conceived. Ancient societies in Mesopotamia, Egypt, and China built primitive dams and canals to control rivers for irrigation, allowing agriculture to thrive and supporting the growth of cities and empires. These early structures were not designed to generate power in the modern sense, but they represented the first step in the long journey of water control that would eventually lead to hydroelectricity. The concept of using flowing water to perform mechanical work appeared in the form of water wheels, which were used by the Greeks and Romans as early as the 1st century BCE. These wheels harnessed the kinetic energy of rivers to grind grain, saw wood, or operate simple machines. In medieval Europe, water mills became widespread and formed the backbone of local economies by providing a steady and reliable source of mechanical energy. For centuries, the water wheel remained one of the most important power technologies available, demonstrating that moving water could replace human or animal labor in many essential tasks. The transition from mechanical power to electrical power began in the 19th century during the Industrial Revolution, when rapid advances in engineering, metallurgy, and science provided the tools to reimagine water's potential. The invention of the dynamo, a machine capable of converting mechanical energy into electricity, was a turning point. Engineers realized that water wheels and later turbines could drive dynamos, creating an entirely new way to produce electricity. The first small-scale hydroelectric plants began to appear in the late 1800s. One of the earliest known was built in Appleton, Wisconsin, in 1882. It used water from the Fox River to power a generator that provided electricity to nearby homes and businesses. Although its output was modest, this project marked the beginning of hydroelectricity as a practical reality. In Europe, similar experiments were underway, with plants constructed in countries such as Germany, France, and Switzerland. These early efforts demonstrated that water could be a reliable alternative to coal-fired power in regions with abundant rivers. The late 19th and early 20th centuries saw rapid progress in the design of water turbines. The development of the Francis turbine, designed by James B. Francis in the 1840s, and the Pelton wheel, invented by Lester Pelton in the 1870s, greatly improved the efficiency of converting falling or flowing water into mechanical energy. These innovations allowed engineers to build larger and more powerful plants that could serve growing urban populations and industries. By the early 20th century, hydroelectric dams were no longer just small installations, but massive projects capable of transforming entire landscapes. The construction of large reservoirs behind dams allowed water to be stored and released on demand, providing not only reliable electricity, but also flood control and irrigation benefits. In the United States, projects like the Hoover Dam, completed in 1936 on the Colorado River, symbolized the scale and ambition of modern hydropower. The Hoover Dam was one of the largest engineering projects of its time, creating a reservoir called Lake Mead and providing electricity to millions of people in the southwestern United States. Its construction showcased how hydropower could drive economic growth, support agriculture, and power cities all at once. Around the world, similar projects were undertaken. In Canada, the development of hydropower along rivers such as the St. Lawrence, and later in the provinces of Quebec and British Columbia, established the country as one of the global leaders in hydroelectricity. In Brazil, massive projects on rivers like the Paraná laid the foundation for a power system heavily dependent on hydropower. In Europe, alpine countries such as Switzerland and Austria invested in dams and reservoirs that not only provided power, but also served as strategic assets for national energy security. The mid-20th century marked the golden age of dam construction. Advances in engineering techniques and materials, such as reinforced concrete, enabled the building of ever larger structures. Governments around the world saw hydropower projects as symbols of national progress and modernity. They were often associated with large-scale development programs aimed at electrifying rural areas, stimulating industry, and demonstrating technological prowess. Yet this period also introduced challenges that became more apparent over time. Large dams required the flooding of vast areas, often displacing communities and altering ecosystems. Iconic projects, such as the Aswan High Dam in Egypt, completed in 1970, provided immense benefits in terms of electricity and flood control, but also created ecological problems by trapping nutrient-rich sediments that once fertilized the Nile Delta. As environmental awareness grew in the late 20th century, debates intensified about the social and ecological costs of large hydropower projects. By the 21st century, the history of hydropower had entered a new phase. Instead of focusing solely on building ever larger dams, engineers and policymakers began to emphasize modernization of existing facilities, the development of small-scale and run-of-river projects that minimized environmental impacts, and the integration of hydropower into a broader mix of renewable energy sources. Today, the legacy of hydropower is visible in the thousands of dams and plants operating worldwide, many of which are decades old but still crucial to national energy systems. Their evolution from ancient irrigation structures to modern power stations reflects the broader story of human ingenuity and adaptation. The journey of hydropower is not just about technology, but about the relationship between societies and the natural environment. It illustrates how humans have learned to harness the immense power of water, while also confronting the consequences of altering rivers and landscapes. Looking back, the history of dams and hydropower plants tells us that progress always comes with trade-offs, and that the lessons of the past continue to shape the future of renewable energy. The fundamental principles that make hydroelectric power possible are rooted in the simple physics of water flow and the conversion of potential energy into kinetic energy and ultimately into mechanical and electrical energy. At the heart of every hydropower system lies the force of gravity, which constantly pulls water from higher elevations to lower elevations. When water is stored in a reservoir behind a dam, it possesses potential energy by virtue of its position above the downstream riverbed. The higher the elevation and the greater the volume of water, the more potential energy is stored in the system. This stored energy is like a battery, created not through chemical reactions, but through the weight of water, held back by a massive structure of concrete and steel. When gates in the dam are opened and water is allowed to flow downward through large pipes called penstocks, this potential energy is converted into kinetic energy as the water accelerates under gravity's pull. The speed and force of the water increase as it moves downwards, and it is this motion that can be directed onto turbine blades to make them spin. The turbine acts as a converter, turning the linear motion of falling water into rotational motion that can drive a shaft connected to a generator. In this way, the chain of energy conversion begins with potential energy at the reservoir, then moves through kinetic energy of flowing water, and finally reaches mechanical and electrical energy that can be transmitted across power lines to homes and industries. The amount of energy that can be produced by a hydroelectric plant depends on two main factors: the flow of the water and the height from which it falls, also known as the head. The flow refers to the volume of water passing through the system, usually measured in cubic meters per second. The head is the vertical distance between the water surface in the reservoir and the turbines below. Together, these two factors determine the total energy available. A plant with a high head, but a small flow, may produce as much power as a plant with a low head, but a very large flow. This is why mountainous regions with steep rivers can support efficient hydropower, even with modest water volumes, while large flat rivers may require massive dams to create the necessary elevation difference. The efficiency of this energy conversion process has been refined through centuries of engineering. Modern turbines can capture more than 90% of the energy in falling water and transform it into usable mechanical energy. This efficiency makes hydropower one of the most effective means of generating electricity from a renewable resource. Unlike other energy sources where much of the energy is lost, as waste heat, hydropower minimizes losses and maximizes the output from the natural flow of rivers. Beyond the technical mechanics, the principles of water flow and energy conversion can be observed in nature itself. Waterfalls, such as Niagara Falls, demonstrate the immense power of falling water, a power that humans have harnessed for more than a century to generate electricity. The roar of a waterfall is a reminder of kinetic energy being unleashed as water crashes from a higher level to a lower one. In a hydroelectric dam, this natural process is carefully controlled and directed so that instead of chaotic splashing, the energy is captured and transformed in an orderly fashion. Another important principle in hydropower is the concept of controlled flow. Unlike a river that runs continuously and unpredictably, a reservoir allows operators to regulate when and how much water is released. This means the energy output can be matched to demand. During times of high electricity demand, more water can be released and more turbines activated. During times of low demand, the flow can be reduced, conserving water in the reservoir for future use. This controllability makes hydropower not only a renewable resource, but also a flexible and reliable one, capable of stabilizing entire power grids. The interaction between potential and kinetic energy also highlights why dam design is so critical. The strength of the dam must be sufficient to hold back the enormous pressure of the reservoir. Every cubic meter of water exerts a force, and when billions of cubic meters are stored, the stresses on the structure become immense. Engineering solutions such as arch dams, gravity dams, and buttress dams are all based on ensuring that the forces of water are safely managed and directed. Without this careful balance, the potential energy stored in the reservoir could become destructive rather than productive. From a broader perspective, the principles of hydropower also remind us of the cycles of nature. The water that fills reservoirs comes from rainfall and snowmelt, driven by the solar cycle and atmospheric processes. This means that hydropower is indirectly a form of solar energy, since it depends on the sun to evaporate water, which later falls as precipitation to refill rivers and lakes. The closed cycle of evaporation, condensation, precipitation, and runoff ensures that water continues to be available for energy production as long as natural climatic patterns persist. Of course, these patterns can vary from year to year, and droughts can reduce the flow of rivers, limiting the availability of hydropower. This vulnerability highlights the need to understand both the physics of energy conversion and the environmental context in which dams operate. In summary, the basic principles of water flow and potential energy form the foundation of hydroelectricity. By storing water at elevation, releasing it in controlled ways, and capturing its motion through turbines, human beings have created one of the most elegant and efficient methods of energy production. The entire system is built on the interplay between gravity, water, and motion, forces that have existed since the beginning of the planet and that continue to sustain life in countless ways. As we move deeper into the workings of dams and hydroelectric plants, it becomes clear that what may seem like a simple concept is in fact a sophisticated application of natural laws. It is this combination of simplicity and effectiveness that explains why hydropower has remained such an enduring and globally important source of energy. The design and structure of dams are central to understanding how hydroelectric power plants function, because the dam itself is the primary mechanism that allows humans to control the flow of rivers and transform water into a reliable source of energy. A dam is essentially a large barrier constructed across a river or stream to hold back water and create a reservoir. But the materials used, the engineering principles applied, and the purpose of the dam determine what type of structure is built. At its core, a dam must perform two critical tasks, which are to withstand the immense pressure of the water stored behind it, and to release that water in a controlled manner so that the flow can be directed through turbines to generate electricity. Throughout history, engineers have developed several main types of dams, each with unique advantages suited to particular landscapes, geological conditions, and purposes. One of the most common designs is the gravity dam, which relies on its own weight to resist the pressure of the water. Constructed typically from concrete or stone, a gravity dam is massive and heavy, pushing down against the foundation to counteract the force of the reservoir. The force of the water tries to push the dam downstream, but the enormous weight of the structure keeps it anchored firmly in place. Examples like the Hoover Dam in the United States demonstrate how gravity dams can reach colossal sizes and serve not only as energy producers, but also as icons of human engineering achievement. A variation of this design is the arch dam, which is curved upstream so that the pressure of the water is transferred laterally into the surrounding canyon walls. Arch dams are more efficient in terms of material usage because they do not rely solely on weight, but instead distribute the force of the reservoir through their shape. They are best suited to narrow valleys with strong rock walls that can absorb the load. The Hoover Dam combines both gravity and arch principles, making it an excellent example of hybrid engineering adapted to the geography of the Colorado River. Another significant type is the buttress dam, which consists of a sloping upstream face supported at intervals by buttresses or triangular supports that transfer the water load to the foundation. This design reduces the amount of material required compared to a solid gravity dam, while still providing the necessary strength to hold back large volumes of water. Buttress dams are less common than gravity or arch dams, but they are practical solutions in areas where reducing material costs is critical. Earthfill and rockfill dams, sometimes referred to as embankment dams, are among the most widely used around the world because they rely on locally available materials like soil rock and clay. These dams are constructed by carefully layering and compacting these materials to create a stable barrier. The core of an earthfill dam is often made from impermeable clay to prevent water seepage, while outer layers of rock or gravel provide structural support. Although they may not look as visually imposing as massive concrete dams, they can be extremely large and are often more economical to build, especially in wide valleys, where using concrete would be prohibitively expensive. The Aswan High Dam in Egypt is a famous example of an embankment dam which has played a critical role in controlling the Nile River and providing both electricity and irrigation. The choice of dam type depends heavily on the geological and environmental conditions of the construction site. Engineers must evaluate the strength of the foundation rock, the width of the valley, the availability of materials, and the expected volume of water to be stored. A poorly chosen design could result in structural failure with catastrophic consequences. So dam construction always involves extensive surveys, simulations, and testing before work begins. In addition to their structural differences, dams also serve a variety of functions beyond electricity generation. Many are multi-purpose projects designed to provide flood control by capturing excess water during rainy seasons and releasing it gradually. Others are built to ensure water supply for irrigation or urban consumption. In some cases, navigation locks are integrated into dam systems to allow ships and boats to pass along rivers that would otherwise be blocked. These diverse roles make dams vital not just for energy, but for broader economic and social development. Recreational and economic benefits are another dimension of reservoirs. Once a river valley is flooded, the new body of water often becomes a site for fishing, boating, and tourism. Many reservoirs are stocked with fish to support local industries or recreational angling. The lakes created by dams can become destinations for visitors, stimulating local economies and providing new opportunities for communities that once depended solely on agriculture or river trade. Despite these advantages, the creation of reservoirs has significant environmental and social consequences that must be carefully considered. Flooding a valley to create a reservoir submerges everything in its path, including forests, farmland, and sometimes entire towns. This process can displace thousands or even millions of people, as seen in the case of the Three Gorges Dam, where entire communities had to be relocated. The social disruption caused by forced relocation can be long-lasting, affecting cultural traditions, livelihoods, and community structures. Ecologically, the impact of reservoirs is equally profound. Damming a river alters its natural flow regime, which affects fish migration, sediment transport, and the overall health of aquatic ecosystems. Species that depend on free-flowing rivers may decline or disappear when their habitats are transformed into still water lakes. Migratory fish, such as salmon, which travel upstream to spawn, face obstacles that can severely reduce their populations. While fish ladders and bypass systems are often installed to mitigate these problems, they are not always effective, and biodiversity can still suffer. Another environmental concern associated with reservoirs is the accumulation of sediments. Rivers naturally carry sediments downstream, but when blocked by a dam, these sediments settle at the bottom of the reservoir. Over time, this can reduce the storage capacity of the reservoir and affect water quality. Downstream regions may also experience reduced sediment supply, leading to erosion of riverbanks and deltas. The trapping of nutrients in reservoirs can further alter ecosystems, both upstream and downstream of the dam. Reservoirs can also contribute to greenhouse gas emissions, despite being part of a renewable energy system. When vegetation is submerged and decomposes underwater, it releases methane, a potent greenhouse gas. This effect is particularly pronounced in tropical regions, where high temperatures accelerate decomposition. As a result, some reservoirs have been found to produce significant amounts of methane, which complicates the perception of hydropower as a purely clean energy source. To address these challenges, Modern dam and reservoir projects increasingly incorporate environmental and social impact assessments before construction begins. Engineers and planners attempt to design systems that minimize displacement, protect ecosystems, and ensure that the benefits of electricity generation are balanced with the costs to communities and nature. In some cases, alternatives such as smaller run-of-river plants, which do not require large reservoirs, are chosen to reduce ecological disruption. Advances in sediment management and fish passage technology also aim to make reservoirs more sustainable. Despite these concerns, reservoirs remain indispensable to hydropower because they provide the stability and flexibility that make this energy source so valuable. They transform rivers, which are inherently variable, into reliable energy systems, capable of supplying baseload power or responding rapidly to peak demand. They protect downstream regions from floods, supply water for human and agricultural needs, and create new landscapes that can support recreation and tourism. However, the story of reservoirs is also a reminder of the trade-offs inherent in large-scale energy infrastructure. The benefits of electricity, flood control, and irrigation must always be weighed against the costs to ecosystems and human communities. In this sense, reservoirs are not only physical structures, but also symbols of the choices societies make when seeking to balance progress with sustainability. As the global demand for renewable energy grows, reservoirs will continue to play a central role, but the way they are designed and managed will determine whether they remain assets or liabilities in the quest for a sustainable energy future. Spillways and gates are critical components of hydroelectric dams because they provide the means to control the movement of water, both during normal operation and during periods of excess flow. Without these mechanisms, a dam would simply trap water indefinitely until it either overtopped the structure or destroyed it by sheer force. The controlled release of water is therefore fundamental to both the safety and functionality of any hydroelectric project. Spillways are essentially overflow structures designed to allow water to bypass the dam when reservoir levels become too high. Recreational and economic benefits are another dimension of reservoirs. Once a river valley is flooded, the new body of water often becomes a site for fishing, boating, and tourism. Many reservoirs are stocked with fish to support local industries or recreational angling. The lakes created by dams can become destinations for visitors, stimulating local economies and providing new opportunities for communities that once depended solely on agriculture or river trade. Despite these advantages, the creation of reservoirs has significant environmental and social consequences that must be carefully considered. Flooding a valley to create a reservoir submerges everything in its path, including forests, farmland, and sometimes entire towns. This process can displace thousands or even millions of people, as seen in the case of the Three Gorges Dam, where entire communities had to be relocated. The social disruption caused by forced relocation can be long-lasting, affecting cultural traditions, livelihoods, and community structures. Ecologically, the impact of reservoirs is equally profound. Damming a river alters its natural flow regime, which affects fish migration, sediment transport, and the overall health of aquatic ecosystems. Species that depend on free-flowing rivers may decline or disappear when their habitats are transformed into still water lakes. Migratory fish, such as salmon, which travel upstream to spawn, face obstacles that can severely reduce their populations. While fish ladders and bypass systems are often installed to mitigate these problems, they are not always effective, and biodiversity can still suffer. Another environmental concern associated with reservoirs is the accumulation of sediments. Rivers naturally carry sediments downstream, but when blocked by a dam, these sediments settle at the bottom of the reservoir. Over time, this can reduce the storage capacity of the reservoir and affect water quality. Downstream regions may also experience reduced sediment supply, leading to erosion of riverbanks and deltas. The trapping of nutrients in reservoirs can further alter ecosystems, both upstream and downstream of the dam. Reservoirs can also contribute to greenhouse gas emissions, despite being part of a renewable energy system. When vegetation is submerged and decomposes underwater, it releases methane, a potent greenhouse gas. This effect is particularly pronounced in tropical regions, where high temperatures accelerate decomposition. As a result, some reservoirs have been found to produce significant amounts of methane, which complicates the perception of hydropower as a purely clean energy source. To address these challenges, modern dam and reservoir projects increasingly incorporate environmental and social impact assessments before construction begins. Engineers and planners attempt to design systems that minimize displacement, protect ecosystems, and ensure that the benefits of electricity generation are balanced with the costs to communities and nature. In some cases, alternatives such as smaller run-of-river plants, which do not require large reservoirs, are chosen to reduce ecological disruption. Advances in sediment management and fish passage technology also aim to make reservoirs more sustainable. Despite these concerns, reservoirs remain indispensable to hydropower because they provide the stability and flexibility that make this energy source so valuable. They transform rivers, which are inherently variable, into reliable energy systems, capable of supplying baseload power or responding rapidly to peak demand. They protect downstream regions from floods, supply water for human and agricultural needs, and create new landscapes that can support recreation and tourism. However, the story of reservoirs is also a reminder of the trade-offs inherent in large-scale energy infrastructure. The benefits of electricity, flood control, and irrigation must always be weighed against the costs to ecosystems and human communities. In this sense, reservoirs are not only physical structures, but also symbols of the choices societies make when seeking to balance progress with sustainability. As the global demand for renewable energy grows, reservoirs will continue to play a central role, but the way they are designed and managed will determine whether they remain assets or liabilities in the quest for a sustainable energy future. Spillways and gates are critical components of hydroelectric dams because they provide the means to control the movement of water, both during normal operation and during periods of excess flow. Without these mechanisms, a dam would simply trap water indefinitely until it either overtopped the structure or destroyed it by sheer force. The controlled release of water is therefore fundamental to both the safety and functionality of any hydroelectric project. Spillways are essentially overflow structures designed to allow water to bypass the dam when reservoir levels become too high. Gates, on the other hand, are mechanical devices that regulate how much water passes through penstocks or spillways to turbines and downstream channels. Together they form the system that transforms a dam from a static barrier into a dynamic water management tool capable of responding to seasonal changes, floods, and electricity demand. The simplest type of spillway is the uncontrolled overflow spillway, where water flows freely over a crest when the reservoir rises above a certain level. This type is often used in smaller dams or in cases where the volume of floodwater is relatively predictable and can be safely managed without active operation. Larger dams, however, almost always include gated spillways, which give operators the ability to regulate outflows precisely. These gates are massive steel structures that can be raised or lowered to release water when necessary. They come in different designs, such as radial gates, also called tainter gates, which rotate on arms to allow water to pass beneath, or vertical lift gates, which are raised straight up to open the passage. The engineering behind gates is complex because they must withstand immense pressure from the water while still being operable at a moment's notice. Hydraulic or electric actuators are used to move them, and redundant systems are often installed to ensure reliability. Another type of spillway is the chute spillway, where water is directed down a sloping concrete channel away from the dam. As water flows rapidly down the chute, it can reach extremely high velocities, so energy dissipation structures are included at the base to reduce the erosive force before the water re-enters the river. Still another variation is the shaft spillway, sometimes called a morning glory spillway because of its circular funnel-like shape. In this design, water enters a vertical shaft and is carried through a tunnel to be discharged downstream. These designs are often used where space is limited or where the terrain makes chute spillways impractical. The role of spillways is not limited to emergencies. They are also used to maintain the reservoir at optimal levels for power generation. If too much water is stored, the pressure on the dam increases unnecessarily. If too little water is stored, then electricity production and water supply functions may be compromised. By opening and closing spillways and gates, operators can manage this balance carefully, ensuring that turbines have the right amount of water to generate electricity, while also keeping the dam safe from overtopping. Gates also play a direct role in feeding water to the turbines. Intake gates control how much water enters the penstocks, which lead to the turbines inside the powerhouse. These gates can be adjusted to increase or decrease generation depending on demand. In times of peak demand, more gates may be opened, allowing more water to flow and more turbines to operate. In times of low demand, the flow can be reduced, conserving water for later. This controllability is one of the reasons hydropower is so flexible compared to other energy sources. The safety aspect of spillways and gates cannot be overstated. During extreme weather events, such as heavy rains or rapid snowmelt, rivers may swell beyond their usual limits. If the inflow exceeds the storage capacity of the reservoir, the only way to prevent a catastrophic failure is to release water through spillways. History provides sobering reminders of the importance of this function. Failures of dams due to inadequate spillway design have caused devastating floods, loss of life, and widespread destruction. Modern dam engineering therefore places great emphasis on ensuring that spillways can handle the maximum possible flood, often referred to as the probable maximum flood. This involves complex hydrological studies to predict extreme scenarios and to design spillways with sufficient capacity. Environmental considerations are also linked to spillways and gates. The release of water affects downstream ecosystems, fish habitats, and communities. Releasing too much water suddenly can cause erosion, disrupt aquatic life, or flood downstream settlements. Releasing too little can reduce river flow, harming ecosystems and limiting water availability for agriculture or urban needs. For this reason, modern hydropower plants often coordinate releases with environmental flow requirements, which aim to mimic the natural variability of rivers to support ecosystems while still producing electricity. Fish passage systems are sometimes integrated into spillways or alongside gates to allow migratory species to bypass the dam. This reflects the growing awareness that dams must not only generate power, but also coexist with ecological systems. Technological advances have improved the way spillways and gates are operated. Remote monitoring systems, sensors, and automated controls allow dam operators to adjust flows with precision in response to changing conditions. Weather forecasting and river monitoring are combined with computer models to predict inflows and optimize gate operations. In many large projects, control centers can adjust gates hundreds of kilometers away, ensuring rapid response to emergencies or changing demand on the grid. Despite all of these innovations, the principles remain grounded in the simple need to manage water safely. The massive weight and pressure of stored water make dams inherently hazardous if not carefully controlled. Spillways and gates are the release valves that keep these systems stable, protect downstream areas, and make hydropower possible. They represent the intersection of engineering precision, environmental responsibility, and operational vigilance. Without them, no dam could safely function as part of a hydroelectric system. In summary, spillways and gates embody the dual role of dams as both sources of energy and guardians of safety. They allow reservoirs to serve multiple purposes while ensuring that excess water does not compromise structural integrity. They provide the fine control necessary for efficient power generation and for balancing the needs of agriculture, urban supply, and ecosystems. They stand as essential features in the evolution of hydropower technology, reminding us that even as we harness the steady pull of gravity and the flow of rivers, we must always respect the immense power of water and manage it with care. At the heart of every hydroelectric power plant lies the turbine, a remarkable machine designed to capture the energy of moving water and convert it into mechanical motion that can later be transformed into electricity. Without turbines, the immense potential and kinetic energy stored in reservoirs and flowing rivers could not be harnessed in a practical way. The turbine represents the crucial link between the natural force of water and the engineered systems that drive modern electrical grids. Understanding how turbines work requires first appreciating their role as converters. When water is released from the reservoir, it rushes down through penstocks with tremendous speed and force. The pressure and velocity of this water strike the blades or buckets of a turbine, causing them to rotate. This rotation is not random, but carefully engineered so that the maximum amount of energy is transferred from the water to the turbine shaft. Once the shaft begins to spin, it can drive a generator which produces electricity. But the initial step of capturing water's energy happens entirely within the turbine. There are several main types of turbines used in hydroelectric plants, each suited to specific conditions of head and flow. One of the most common is the Francis turbine, named after James B. Francis, who designed it in the 19th century. The Francis turbine is a reaction turbine, meaning it operates fully submerged in water and uses both pressure and velocity to generate motion. Water enters the turbine through spiral-shaped casings called volutes and passes through fixed guide vanes that direct the flow at just the right angle onto the runner blades. These blades are curved to maximize efficiency, and as water flows across them, it imparts energy that causes the runner and shaft to rotate. Francis turbines are highly versatile and can operate over a wide range of heads and flows, which makes them the workhorse of the hydroelectric industry worldwide. Another important design is the Pelton turbine, an impulse turbine invented by Lester Pelton in the late 19th century. Unlike reaction turbines, Pelton wheels operate in air and are driven by jets of water, striking spoon-shaped buckets mounted on the wheel's circumference. The design ensures that the water jet changes direction almost completely as it strikes the bucket, transferring nearly all of its energy to the wheel. Pelton turbines are especially suited for high-head, low-flow sites, such as steep mountain rivers, where water can be channeled through long penstocks to build up pressure before striking the wheel. They can achieve very high efficiencies and are often used in alpine regions or areas with significant elevation differences. A third common design is the Kaplan turbine, which resembles a giant ship propeller and is another type of reaction turbine. Invented by Victor Kaplan in the early 20th century, this turbine features adjustable blades that can change angle depending on the flow of water. This makes Kaplan turbines ideal for low-head, high-flow situations such as large rivers or tidal plants. Their adaptability allows them to maintain high efficiency across varying water conditions, which is particularly useful in rivers with seasonal changes. The choice of turbine type depends on careful analysis of site conditions, including available head, expected flow, and desired generating capacity. Engineers use complex models to predict how different turbine designs will perform and select the one that ensures maximum efficiency and reliability. In many modern hydroelectric stations, multiple turbines of different types or sizes may be installed to accommodate a wide range of operating conditions. Beyond their basic design, turbines are feats of precision engineering. The blades must be shaped to exact curves so that water flows smoothly without creating turbulence or cavitation, which can damage the metal surfaces. Cavitation occurs when pressure drops low enough for bubbles to form and then collapse violently against the blades, causing pitting and erosion. Engineers combat this by selecting the right materials, such as stainless steel, and by designing blade shapes that minimize sudden pressure changes. Turbines also require robust support systems, including bearings, lubrication, cooling, and control mechanisms, to ensure continuous operation under immense mechanical loads. In addition to their mechanical function, turbines are central to the efficiency of the entire hydropower plant. Modern turbines can convert more than 90% of the water's energy into mechanical motion, making hydropower one of the most efficient energy technologies in existence. This efficiency has been refined through decades of experimentation, modeling, and improvements in metallurgy and manufacturing techniques. Computer simulations now allow engineers to design blades that are optimized for fluid dynamics down to the smallest detail. The operation of turbines is closely coordinated with reservoir management and electrical demand. Operators can start or stop turbines within minutes by opening or closing intake gates, allowing hydropower to provide rapid responses to fluctuations in grid demand. This flexibility distinguishes hydroelectricity from many other sources of energy which require longer startup times. For example, a coal plant may take hours to ramp up, while a hydro turbine can begin generating power almost immediately once water begins to flow. This responsiveness makes turbines not only machines of energy conversion, but also tools of grid stability. Environmental considerations are also linked to turbine operation. As water passes through turbines, its velocity and pressure change, which can affect fish and aquatic life. In response, Engineers have developed fish-friendly turbine designs with smoother blade edges, slower rotation speeds, and improved flow patterns to reduce harm to organisms. These innovations reflect a growing recognition that hydropower systems must balance energy generation with ecological responsibility. Looking at turbines across history reveals their symbolic role in human progress. From early water wheels that ground grain to today's precision-engineered turbines capable of powering entire cities, the principle remains the same: converting the motion of water into useful work. The scale and sophistication may have changed, but the underlying concept demonstrates how humanity continues to harness nature's forces with ingenuity and care. In summary, turbines are the heart of hydroelectric dams, transforming water's potential and kinetic energy into mechanical energy with remarkable efficiency. They exist in multiple forms, such as Francis, Pelton, and Kaplan, each designed for specific conditions and refined through centuries of engineering advancement. They operate not only as machines, but as guardians of balance between nature and human need, ensuring that the immense power of rivers is captured safely, efficiently, and sustainably. Without turbines, the reservoir would be nothing more than a lake behind a wall, but with them, the dam becomes a dynamic system that powers homes, industries, and entire nations. The generator is the crucial component that allows the motion of water captured by turbines to be converted into the form of energy that powers modern civilization: electricity. While the turbine translates the kinetic and potential energy of water into mechanical rotation, it is the generator that takes this rotation and transforms it into electrical current that can be transmitted across power lines to homes, factories, and cities. The principle behind generators is rooted in the discoveries of electromagnetic induction made in the 19th century by scientists such as Michael Faraday. Faraday showed that when a conductor moves through a magnetic field, it induces an electric current within the conductor. This principle remains the foundation of virtually all large-scale electricity generation, whether in coal plants, nuclear stations, wind turbines, or hydroelectric facilities. In a hydroelectric generator, the turbine shaft is connected to a rotor, which is the moving part of the generator. The rotor carries a series of powerful magnets, or in some designs, electromagnets. Surrounding the rotor is the stator, which is the stationary part of the generator and is made up of coils of copper wire. As the rotor spins, due to the force of the turbine blades, the magnetic field created by its magnets sweeps past the copper coils. This motion induces an alternating current in the coils, which can then be harnessed as electricity. The alternating current is particularly important because it can be easily transformed to different voltages, allowing for efficient transmission over long distances. The size and scale of hydroelectric generators are immense compared to everyday machines. A single generator in a large dam may weigh hundreds of tons and be several stories tall. The shafts connecting the turbines to the rotors can be as thick as a tree trunk and rotate at hundreds of revolutions per minute. The entire system must be carefully balanced because even the slightest misalignment at such scales can create vibrations that damage equipment. Engineers therefore design these machines with extraordinary precision and use advanced bearings and lubrication systems to ensure smooth rotation. Cooling is another critical factor in generator operation. as current flows through the coils of the stator heat is produced due to electrical resistance. If this heat is not dissipated, it can damage insulation or even melt components. To prevent this, many generators are equipped with elaborate cooling systems that use air, water, or hydrogen gas to carry heat away from the stator and rotor. Hydrogen cooling is especially effective because the gas has high thermal conductivity and low density, which reduces friction and energy losses. Control systems are integrated into generators to regulate voltage frequency and stability. When a generator begins operating, the magnetic field in the rotor must be carefully excited by supplying a small initial current, often from an external source. Once the generator is synchronized with the grid, it can feed its electricity into the system. Synchronization is vital because the grid operates at a specific frequency, such as 50 Hz in Europe or 60 Hz in North America. If a generator feeds power at the wrong frequency, it can destabilize the grid or damage equipment. Operators use sophisticated instruments to ensure that each generator comes online in perfect synchrony with the existing electrical network. The reliability of hydroelectric generators is one of their greatest strengths. Unlike small engines or intermittent renewable systems, generators in dams can run continuously for months at a time, with only periodic maintenance. Many hydroelectric stations built decades ago still operate today, with their original generators having undergone refurbishments and upgrades. This longevity makes hydroelectricity not only efficient, but also highly economical over the long term. Advances in materials science and engineering have further improved generator performance. Modern copper alloys reduce resistance and improve conductivity, while stronger steels allow for more compact and durable rotors. Computer modeling enables engineers to design magnetic fields that maximize induction while minimizing losses. Digital monitoring systems now track vibrations, temperatures, and electrical outputs in real time, allowing operators to detect problems early and prevent costly breakdowns. Generators also play a role in grid stability beyond simply producing electricity. Because they are large rotating masses, they contribute to what engineers call inertia, which helps stabilize the frequency of the power grid. When demand or supply fluctuates suddenly, the inertia of spinning generators resists rapid changes, keeping the system steady. This stabilizing effect is becoming more valuable as grids incorporate more variable renewable sources like wind and solar, which do not inherently provide the same inertia. Hydroelectric generators thus act not only as sources of power, but as anchors of reliability for entire energy systems. Environmental and social considerations intersect with generators in subtler ways compared to turbines or reservoirs, yet they remain important. For example, the noise and vibrations created by massive generators can affect nearby communities if not properly managed. Careful design of housings and dampening systems helps minimize these impacts. The efficiency of generators also contributes indirectly to sustainability, because the more effectively they convert mechanical energy into electricity, the less water is needed to produce a given amount of power. In developing regions, hydroelectric generators have had transformative impacts by enabling electrification of rural areas and industries. Small-scale hydro plants, equipped with smaller but similar generators, can provide reliable power to villages far from national grids, stimulating economic activity, education, and healthcare. In this way, Generators are not just mechanical devices, but tools of social development and progress. The future of hydroelectric generators lies in continued modernization. Many existing plants are upgrading their generators with new materials and digital controls to improve efficiency and extend their lifespan. Some projects explore reversible generators that can operate as motors in pumped storage systems, allowing water to be pumped back into reservoirs during times of low demand and released again to generate electricity when needed. This adaptability highlights how generators remain central to balancing modern energy systems. In conclusion, the generator is the heart of the hydroelectric conversion process, taking the raw mechanical energy provided by turbines and turning it into the electrical energy that powers the world. Its operation rests on the elegant principle of electromagnetic induction, yet its execution involves machines of immense size, complexity, and precision. Generators represent both the ingenuity of 19th century scientific discovery and the enduring engineering achievements that continue to sustain our energy needs today. Without them, the controlled flow of rivers and the rotation of turbines would remain mechanical curiosities. But with them, the energy of water becomes the lifeblood of modern society, flowing through wires into every aspect of our daily lives. Once water has been released from the reservoir, spun the turbine, and driven the generator, the process of creating electricity is complete only at the local level of the power station. For hydroelectric power to be useful to society, it must travel across vast distances to reach homes, businesses, and industries. This process, known as transmission and distribution, forms the vital network that transforms the energy of a single river into a resource that sustains entire nations. Transmission begins at the hydroelectric plant itself, where the electricity generated by the large turbines and generators is produced as alternating current at relatively low voltage, often in the range of a few thousand volts. While sufficient for short distances, this voltage level is not suitable for long-distance transmission because much of the energy would be lost as heat due to resistance in the wires. To address this, transformers located at the power station step up the voltage to extremely high levels, sometimes exceeding several 100,000 volts. By increasing voltage and simultaneously decreasing current, the amount of energy lost to resistance is minimized, making it possible to send power hundreds or even thousands of kilometers efficiently. The high-voltage electricity then travels along transmission lines that span valleys, mountains, and plains. These lines are supported by tall steel towers, or pylons, that keep the conductors elevated and insulated from the ground. The scale of these transmission networks is enormous, and they often cross national borders, enabling countries to trade electricity or balance supply and demand across regions. Hydroelectric power is particularly valuable in such networks because it can be dispatched quickly, helping stabilize systems that also rely on more variable renewable sources like wind and solar. Transmission lines eventually reach substations where the voltage is stepped down again using transformers, so that the electricity can be distributed safely to consumers. From the substation, distribution lines carry power into cities, neighborhoods, and rural areas. These lines are often seen running overhead along streets or buried underground in urban areas. At this stage, the voltage is reduced further, down to the levels used in everyday appliances and equipment, such as 120 volts in North America or 230 volts in much of Europe. The journey from turbine to household outlet may span only a few kilometers in some cases, but in others, It can involve networks that stretch across entire continents. The infrastructure supporting transmission and distribution is more than just wires and transformers. Advanced control systems are required to monitor flows, detect faults, and ensure stability. Modern hydroelectric systems are often integrated into smart grids, where sensors and automated controls continuously adjust to changing conditions. For example, if a sudden surge of demand occurs on a hot summer day when millions of air conditioners are switched on, hydroelectric plants can release more water through their turbines and feed additional power into the grid within minutes. This rapid response capability is one of the reasons hydroelectric power remains such a cornerstone of modern electricity systems. Transmission and distribution also involve challenges of synchronization. Because electricity in a given grid must operate at a fixed frequency, all generators feeding into that grid must work in unison. Hydroelectric generators must therefore be carefully coordinated with other sources such as coal plants, nuclear stations, wind farms, and solar arrays. This synchronization ensures that when lights are switched on or machines are started, the electricity is delivered smoothly without surges or drops. The reliability of hydroelectric power makes it particularly important for providing baseload supply as well as backup during periods of peak demand. Beyond the technical aspects, transmission and distribution networks represent the social reach of hydroelectricity. They are the means by which the energy stored in a remote reservoir high in the mountains can illuminate a distant city, power a factory, or charge a smartphone hundreds of kilometers away. In many countries, the construction of transmission lines alongside hydroelectric projects has been transformative, bringing electricity to rural areas for the first time and stimulating economic development. Electrification has historically been linked to improvements in education, healthcare, and overall quality of life. And hydroelectric projects have often been at the forefront of these advances. Yet the expansion of transmission and distribution networks also raises environmental and social questions. Transmission lines require corridors of cleared land that can affect forests, wildlife habitats, and agricultural areas. The construction of such infrastructure may involve relocating communities or altering landscapes. Careful planning and impact assessments are therefore necessary to minimize disruption. In recent years, efforts have been made to design more environmentally friendly transmission systems, such as burying lines underground where feasible or using advanced tower designs that reduce land use. Another consideration is the resilience of transmission and distribution systems. Natural disasters such as storms, floods, and earthquakes can damage lines and substations, leading to widespread blackouts. Hydroelectric power plants themselves are often located in regions prone to such risks, such as mountainous areas subject to landslides or valleys vulnerable to flooding. Designing robust networks with redundancies and backup systems is therefore crucial to ensuring that hydroelectric power continues to serve communities even in times of crisis. As global energy systems evolve, transmission and distribution remain central to integrating hydropower with other renewable sources. One of the most promising developments is the use of long-distance high-voltage direct current (HVDC) transmission lines, which are more efficient over thousands of kilometers compared to traditional alternating current lines. HVDC technology makes it possible to connect hydroelectric plants in remote regions, such as the rivers of Canada or the highlands of South America, to distant urban centers where electricity demand is greatest. This integration of distant resources into unified grids represents a new frontier in renewable energy management. In conclusion, the transmission and distribution of hydroelectric power are the final steps in a long chain that begins with the gravitational pull of water stored in a reservoir. Through transformers, transmission lines, substations, and distribution networks, the energy of falling water is transformed into a resource that lights homes, drives industries, and powers daily life. These systems embody both the technical precision and the social vision required to harness natural forces for human benefit. They remind us that hydroelectricity is not confined to the walls of a dam, but is part of a vast and interconnected network that links rivers to cities and natural cycles to human progress. Without transmission and distribution, the energy of water would remain locked within remote valleys, but with them, it becomes one of the great engines of modern civilization. The future of hydropower is shaped by a combination of technological innovation, environmental responsibility, and the urgent need to transition towards sustainable energy systems. While hydropower is already the largest source of renewable electricity in the world, it faces significant challenges that must be addressed if it is to continue playing a vital role in global energy strategies. At the core of the debate lies the balance between hydropower's benefits as a renewable and low-carbon energy source and its potential costs in terms of environmental and social impact. On the one hand, hydropower provides stable baseload power and can be ramped up quickly to meet peaks in demand, making it an indispensable tool for stabilizing modern grids that increasingly rely on variable renewables like wind and solar. On the other hand, large dams can disrupt ecosystems, displace communities, and alter river systems in ways that are not easily reversible. The path forward therefore requires rethinking how hydropower is planned, built, and managed in the 21st century. One of the most promising developments is the modernization of existing facilities. Many dams around the world were built decades ago, and while they continue to operate, their turbines, generators, and control systems may not reflect the efficiencies achievable with modern technology. Upgrading these components can significantly increase output without the need to build new dams. In some cases, refurbishments have raised the efficiency of plants by more than 10%, which translates into enough additional electricity to power entire cities. Modern sensors and digital monitoring systems also make it possible to detect wear and inefficiencies early, reducing maintenance costs and improving reliability. Another area of growth lies in small-scale and run-of-river hydropower projects. Unlike massive reservoirs that flood large areas, these smaller installations divert only a portion of river flow through turbines before returning it downstream. While they generate less power individually, they can be deployed widely in suitable rivers, particularly in remote areas where grid connections are limited. Their smaller footprint reduces environmental and social impacts, making them more acceptable to communities and regulators. In developing countries, such projects are seen as tools for rural electrification and local economic development, bridging the gap between isolated communities and national energy systems. Pumped storage hydropower is another critical innovation shaping the future. In this system, water is pumped from a lower reservoir to an upper reservoir during times of low electricity demand when surplus energy is available, such as at night or when wind and solar generation exceeds demand. Later, When electricity demand rises, the stored water is released back down through turbines to generate power. This effectively turns hydropower into a giant battery capable of storing renewable energy and releasing it when needed. As more wind and solar capacity is added to grids worldwide, pumped storage is becoming increasingly important for maintaining stability and ensuring reliable supply. Environmental challenges remain significant, and the future of hydropower must address them directly. Sediment buildup in reservoirs reduces storage capacity and can shorten the lifespan of dams. Innovative sediment management techniques, such as sediment, bypass tunnels, and controlled flushing, are being developed to keep reservoirs functional for longer. Fish migration is another issue that continues to attract attention, as many species depend on free-flowing rivers for spawning. Improved fish ladders, bypass systems, and even fish-friendly turbines are being introduced to reduce ecological disruption. Climate change adds another layer of complexity. Altered rainfall patterns, melting glaciers, and changing snowmelt cycles can affect river flows, reducing the reliability of hydropower in some regions. In areas that depend heavily on seasonal snowpack to feed rivers, the shift to warmer winters and earlier snowmelt may reduce summer flows when electricity demand is high. Conversely, more intense rainfall events may increase risks of flooding and dam stress. This means hydropower infrastructure must be designed and managed with greater flexibility, incorporating climate models and adaptive strategies to remain resilient in the face of uncertain future conditions. Social acceptance of new hydropower projects is also a defining factor for the future. Large-scale projects that displace communities or flood culturally important areas often face strong opposition. For hydropower to remain viable, it must be developed in ways that respect local populations, provide equitable benefits, and minimize harm. Participatory planning processes, fair compensation, and investments in local development are now seen as essential elements of any new project. International guidelines, such as those from the World Commission on Dams, emphasize that the voices of affected communities must be heard in decision-making. Technological innovation will continue to shape hydropower's evolution. Advances in materials may lead to lighter, stronger turbines and generators with reduced maintenance needs. Digitalization will allow more precise control of flows and faster integration with smart grids. Hybrid renewable projects that combine hydropower with solar or wind at the same site are being tested, allowing shared infrastructure and greater efficiency. Floating solar panels installed on reservoirs are an example of this trend, reducing evaporation while providing additional renewable energy capacity. The geopolitical dimension of hydropower is also likely to grow in importance. Rivers often cross national borders, and large dams upstream can affect water availability downstream. This can lead to tensions between countries, but it can also create opportunities for cooperation if projects are managed transparently and benefits are shared. International river basin agreements and joint development projects may become increasingly necessary to ensure hydropower supports not only energy security, but also regional stability. Looking ahead, the role of hydropower will not diminish, but it will change. It will increasingly act as a stabilizing partner to other renewables, providing flexibility, storage, and reliability. Large new dams may become less common due to environmental and social concerns, while modernization of existing infrastructure, expansion of small-scale plants, and growth of pumped storage facilities will define the sector. In this way, hydropower will continue to serve as both a cornerstone of renewable energy and a bridge to a fully sustainable future. In conclusion, the future of hydropower is not just a technical question, but a societal one. It asks how humanity can continue to harness the ancient force of flowing water in ways that meet modern needs without sacrificing ecosystems or communities. The answers lie in innovation, adaptation, and responsibility. By improving technology, addressing environmental impacts, planning inclusively, and integrating hydropower into broader renewable strategies, this resource can remain a vital part of global energy systems. Hydropower's legacy is long, and its future will depend on our ability to balance progress with stewardship, ensuring that the rivers, which have sustained civilizations for millennia, continue to provide energy, stability, and life for generations to come.